In this video, we'll be discussing the application of conservation of mass for a control volume to real-world systems. So we're going to hark back to learning objective 26, which used Reynolds transport theorem, and we're going to use that Reynolds transport theorem and apply it to conservation of mass. Okay. So remembering from learning objective 26, we were able to simplify Reynolds transport theorem for steady uniform flow at the inlet and exit to be the change of an extensive property over time within a system is equal to the summation at the exits of the mass flow rate times specific property minus the summation at the inlets of the mass flow rate times specific property. So on the left side we have all of that change of our extensive property in the system, and on the right side we have that net flow, how much has come into and out of our control volume through those control surfaces. Okay, so applying that to conservation of mass, in this case we're going to say that mass is our extensive property, capital letter B. Well, then if our lowercase letter b is our specific property, that's just going to be mass divided by mass, which is going to be 1. So if we plug that into our Reynolds transport theorem, we get the change in mass of the system over time is equal to the summation at the exit of the mass flow rate times 1 minus the summation at the inlets of the mass flow rate times 1. Now remember from when we defined that, well, remember that for the Reynolds transport theorem, the left side of the equation you can think of almost as a closed system. We're accounting for all the mass. Remember, for closed systems we said the mass doesn't change over time. So if the mass isn't going to change over time, then we can really say that on the left side that's going to be 0, because we're going to account for it all. So it can't go away. It has to be all there. Well, what that means is we can then rewrite the equation. We just move the summation at mass flow at the inlets to the left side. We're going to change some of the nomenclature. We're going to use lower subset i's for inlets and subset e's for exits. And what you get is this very simple equation. The summation of the mass flow rate at the inlet is equal to the summation of the mass flow rates at the exit. This is equation 3.20b. It's also on your reference data card. All right. So it's kind of almost intuitive that the mass all has to go somewhere. It doesn't just evaporate out. It doesn't go away. We have to account for it. It doesn't just disappear. But this is our mathematical proof of conservation of mass. And so this is how one of the tools we're going to use in a control volume situation. So let's apply this to an example problem. We're going to use example problem 3.4. So in example problem 3.4 we have steam and water mixing to provide preheated water. Alright, so it's all water in some form. So what they're asking us to find is the cross-sectional area in centimeters squared of the pipe through which the water is going to exit. Okay, so that means the areas, cross-sectional areas of these pipes are going to change. They give us a diagram and data. It's shown below. So we have the liquid water and the steam coming into the mixing chamber, and we have preheated water coming out. Some assumptions we're going to have to make. Well, in order to use the more simplified equations that we have, I don't want to have to deal with integrals, so I'm going to make the assumption that we have steady flow and uniform exit inlets. That's going to get rid of those integrals, so I can then use the more simplified conservation of mass. So they want us to find the area at 3. Well, let's look at what we have about 3. We have density, we have velocity. If we try and look on a reference data card for something that involves area, you'll see that we have the equation. It's underneath the conservation of mass for one inlet, one exit, but it applies to multiple exits as well. And that is that the mass flow rate is equal to density times area times velocity. That's true of any mass flow rate at a point. Okay, so at 1 and 2, we can apply that equation as well. The other thing, so we have density, we have velocity, but we don't have the mass flow rate. So the other thing we're going to have to use to solve this is our conservation of mass, which is the sum of the mass flow rates coming into the system, which is the mixing chamber. You can see the dotted line is drawn around the mixing chamber, is equal to the sum of the mass flow rates exiting. So with these two equations, we should be able to solve this problem. All right. So let's apply these. So we're going to make this more specific. So mass flow rate at point 3 is equal to density at 3 times area, cross-sectional area at 3 times velocity at 3. Well, we want to solve this in terms of area, so we're going to say rewrite this equation. So area, cross-sectional area 3 is equal to mass flow rate 3 divided by density at 3 times the velocity at 3. Okay. But we don't have mass flow rate 3, so we're going to use conservation of mass. So we have two inlets, 1 and 2, so mass flow rate 1 plus mass flow rate 2, and that's going to equal our exit. All right. It's all got to go somewhere. If we combine these equations, we can get that area, cross-sectional area at 3 is going to equal to mass flow rate 1 plus mass flow rate 2 divided by the density at 3 times the velocity at 3. So let's plug some numbers in. Key to remember is we need to do our conversions, because it wants the answer in centimeters squared, and this is going to give it to us in meters squared. Now, I don't always remember my relationship for areas. I don't remember exactly what meters squared is related to centimeters squared, so I just broke it up, and I said 100 centimeters times 100 centimeters, because I know 100 centimeters is 1 meter. Okay. When we do that, put it all into the calculator, what we get is 14.7 centimeters squared. Okay, so this is how you would apply conservation mass in a control volume to a real-world problem.